Yeah, hello everyone. Today I'm talking about multiple sequencing alignment, which is very essential in the modern day molecular biology with the sequencing. For many reasons, one most prominent example is probably Alphafold, because through utilizing MSAs, it was able to have like an insane performance. And I guess revolutionized this field. So this is the one part. And last year's for proteins, RNA, and then for DNA, for like evolutionary trees and everything. Those are the main three things. And this is the horizontal and the vertical, which we will talk about. Is first I will go a little bit more into the specific use cases, and then I will go into the cost functions you use, and then the quality, and kind of then in the last step I will talk about a little bit of the optimization of the algorithms so that they can run efficiently. For the DNA, let's start by that. It's like the evolutionary thing. What you want to do is figure out how evolutionary distant two things are from each other, or several things are from each other. Multiple sequencing alignments, I should add, is every alignment which is where you align more than two sequences. RNA, generally, this alignment is then it's like sequence assembly, creating like a consensus sequence which has very high quality, and that you don't miss things which you might have missed if you just do pairwise alignment. And then largely proteins, for the proteins, what is important is that you have you can align them, and you can kind of figure out first whether one new protein belongs to a protein family, but then also kind of just creating those families in the first place, and figuring out the similarity. And sometimes there are things which are being missed, and if you would just test whether this one sequence has a similarity with all the each of those other sequences, as compared to whether there are some general similarity, constant similarities across all of those other sequences. Yes. Okay, so for the next thing, let us go into the cost functions. If you do an alignment, you can have different alignments depending on what cost functions you choose, and of course there's a lot of variance. You have you want to limit this for one to something smaller. There's for proteins, they have roughly a 40% similarity score, and this it's easy to align them, but if it's going down to 25%, it's relatively hard, even though they can still be homologous. They can still be homologous because just certain motifs need to match, and the thing is the alpha helices and everything, secondary structures, which I talk about in my previous video, they yeah, those are like, I mean, they can have variable like proteins in them, and or like amino acids in them, and but still can still be very similar. Yeah, so cost functions. Oh yeah, so all you do is like, it's very simple. You have a list of sequences, and then you check like for one character, how does it fit the best, and this is all, and then you can of course like assign different costs to each of the differences. I'll probably also show an example here. Yeah, so that's the first function, and then the second, you can do like a profile alignment where you have a lot of sequences, and what you do then is you say like, okay, so you have you kind of, I guess, summarize it. And what you do is like, so if you have like 3 sequences and 2 of them have like the A in the first column, then what you would do is you would just say like it's a bad example, but like 67% of them have 67% of them have the A. So instead of like going through each of them, what you would do is just say like multiply this number, and then you have like a weighted sum of pairs in a way, and then it's like, I guess it's speeding it up, and speeding it up, and then also the other and then we have the weighted sum of pairs again, but there's like, you check the question you try to answer is how different within those are those sequences to each other, because there you compare each sequence to one another, and of course this has a relatively I mean, it's like it works in O of 1n squared, and yeah, so those are the three things, and you kind of assign like one sequence a specific value. Yeah, so
Oh, is this your creation? I helped with the electronic, but very cool. Yeah, it's great. There were, is there a public Git repo with the like? Yeah, that's one thing. The first one I picked up is something. Is the rest? Some folks were like, "Oh, this is so cool," and they were like, "I wonder if there's a way to that there was like a power debug prompts that I think yeah, not a case, sir. I'm right now getting a third like filtering is the problem.
yeah, one issue with all of the scores is kind of the conservation is not included as like a penalty or as a score for for like for a column. So that is one issue. And yeah, you can see this like if the sequence gets longer, that like whether you have like one nucleotide which you add just different or not. It doesn't make that much of a difference in the algorithm anymore, like, relatively speaking. But if you, it makes a big difference biologically. So that's one thing, and the other thing is how to handle gaps, because like I find um, gaps, um, find gap costs, because you want those to be smaller, but on the other hand, um, if if it has like gaps everywhere, then it's a little bit of an issue, because yeah, then it's like just more gaps. So like you, yeah, I mean because it's like not biologically relevant if you have like just one row completely filled with gaps. Um, and so that is kind of why you then add the additional cost of um, like if a gap is completely enclosed within another gap, then you add like an additional cost into this quasi affine. It yeah, it just has a little bit of a higher cost to add an additional gap than the quality assessment. At first glance, it seems easy. You kind of just you have to constrain the space uh, for the alignment, and then you can kind of just check visually how similar it is. But it's not as similar because, I mean, for one, like sometimes there are uh, specific motifs which are very important, or like alpha helices which are important. So that is one issue. Another issue is if you're trying to like figure out whether a sequence is like evolutionary related and they are very distant from one another, you might not be able to see that. And yeah, I think those are the main things. And yeah, then you want to have like kind of you kind of I guess check the quality benchmarks which are being used. Do focus on the yeah, just like on the conservation, because it's like just most obvious thing. And there was like a benchmark which curated this manually, something called Bali something, and there they kind of compared the different algorithms, and luckily enough there are yeah algorithms which perform very well. I mean, I think the Costa W it even yeah got 100% or like 98% Corsa. Um, yeah, so that is something um, why I think people are relatively confident in those multiple sequencing alignments. Alright, for as to how like what algorithms you can use for the alignment, or like what ideas you can use. You can either kind of do it progressively, where you start with one align, like with multiple, like a few alignments, align those, um, and then align additional ones to those, and hope that yeah, they kind of stay the same and don't miss major things. And then you also have the iterative solution where you start also with a few, but then you um, you add more, but you kind of yeah cut cut it up or separate it, and kind of just look at those for the alignment. Um, so that is the second one. Then there's also the option to divide and conquer, where you yeah just like find good cutting positions and then cut there and then align there. So it's similar to the iterative one, except that you find the cutting positions first and directly align perfectly, or like, yeah, within bounds, and then, yeah, you kind of, there's the option to not use any heuristics. Like, I mean, um, a thing which doesn't use any heuristic is just like an exact approach which uses dynamic programming, similar to the yeah, Pairwise, but I will go into that later. And then, yeah, this you kind of just combine with the other, like once you have some bounds for the solutions, you can use this. And something. Oh yeah, two things which I missed. One was the um, just don't care about the whole thing and kind of boil it down to smaller parts. And that is you then like just find the core conserved sequences, conserved regions, and use them as anchors to align the rest. This is one, and the other is to use like a probabilistic approach, like hidden Markov models. Um, yeah, of course, there you kind of have the issues like how can you get the probabilities. Um, But yeah, so those are the major ones. Usually you kind of combine them